Hello, and welcome to today's session on hypothesis testing. As always, before we begin, please make sure that you have the PowerPoint lecture notes printed and in front of you so that you can take notes along the way. For our discussion today, we'll begin with the logic of hypothesis testing, and then after that we'll move on to talk about how it is that we evaluate different kinds of hypotheses. And our conversation today is going to be directed most obviously at the science of psychology, yet the hypothesis testing that we have here really works for any of the other sciences as well. So just to set the stage a little bit, let's see if we can remind ourselves of the research cycle. In the science of psychology, the real-world phenomena that we're typically interested in would be behaviors, thoughts, and feelings. We might pick a particular behavior, thought, or feeling for research investigation, and then see if we can abstract from that real-world phenomena some kind of research representation that might be manageable. You'll recall that the abstraction process involves taking some operational definitions and taking some samples so that we have something manageable over here that we can investigate through any of three broad categories of methodology. These would include surveys, or experiments, or observational methods, or perhaps some combination of all of those to produce our research results. Once we have a set of results, we engage in some kind of data analysis. And recently in our video series, we've talked a little bit about frequency distributions, z-scores, and percentiles. Today we're going to be adding to that and trying to understand how we can use z-scores and frequency distributions to evaluate hypotheses. We're essentially going to make a binary decision about whether to reject or not to reject a hypothesis that might be under consideration. That will lead us to some kind of research conclusion that we hope will generalize adequately back to the real world. Okay, so let's talk a little bit about different ways of thinking of hypotheses. In an earlier video, we mentioned that a hypothesis is a testable explanation for a phenomenon. And we described why testability is so important in science, and we've described some of the features that a hypothesis might have that would render it untestable. Here we're going to think about hypothesis just in a slightly different way. We might say that a hypothesis is a statement about the relationship between variables. And we're going to learn about an important hypothesis called the null hypothesis, which basically says that there's no relationship between the variables, that the independent variable is not affecting the dependent variable at all, or the two variables are not at all correlated one with the next. So we'll be talking a little bit statistically now about these variables, and we'll define a variable as an entity that can assume multiple values. It might just be two values, it might be many, many kinds of values, but a variable is an entity that can assume different kinds of values. Whenever we evaluate a hypothesis, there is a chance that we can be making an error. A moment ago I mentioned that we're making a binary decision in our hypothesis testing. We'll either retain, or I should say, reject a hypothesis or fail to reject a hypothesis. Okay? And we might be making different kinds of errors. To minimize those kinds of decisional errors that we might make, and to help other researchers understand the kinds of conclusions that we're drawing in our research, there are some standard procedures that we're going to be learning about. And we're going to divide these into a four-step process. The first step involves stating what the hypothesis is, and we typically have a hypothesis that we call the null hypothesis, that we'll see in a moment is signified by HO, O for null. And by convention, the hypotheses are stated in terms of population parameters. We've met these before. The two most commonly used population parameters are mu and sigma. These correspond to the mean and the standard deviation of the population. And you'll recall that the population is every member of a group of interest. Usually the population is too unwieldy, and as we've seen in our earlier research cycle diagram, we can remind ourselves that we need to get something that's a little bit more manageable. We need to get a sample that represents the overall population, and we might describe that sample using these lowercase English letters like the M for mean or the S for standard deviation. Sometimes we use an X bar, that's an X with a bar over it, to refer to the particular descriptive statistics of the sample. But if we're talking about stating the overall population characteristics, we would use the population parameters, because usually in inferential statistics we're trying to draw an inference about the overall population from a much smaller sample that's a little bit more manageable to work with. Okay, so by convention we state a null hypothesis and something called an alternative hypothesis. So this is a critical piece of symbol or symbolization that you'll have to pick up, and this is that the null hypothesis is given by HO. Okay? The alternative hypothesis is H1. So null would be 0, and 1 is the alternative or the research hypothesis. Okay, and let's see if we can put this into a practical example. Many of us in psychology are interested in this important issue of depression. Depression is a naturally occurring human phenomenon. It actually affects other animals as well. And we have ways of measuring depression in humans, lots of different ways of doing this. One that you might recall from a recent video is the Beck Depression Inventory. And let's just pretend that we have a population of depressed patients in a mental hospital, and their mean Beck Depression Inventory score is something like 26. We can state a null hypothesis about a treatment that we might have for these patients who are depressed. That treatment could be something that's behavioral, it could be something that's cognitive, it could be something that's pharmacological, like Prozac. As you might remember, Prozac is a selective serotonin reuptake inhibitor, or an SSRI, and we can ask about the question of whether Prozac is effective in reducing depression, or in some way altering the depressive state. So if we have the null hypothesis, the HO, what we can say is that we can look at a sample from our population before we give the treatment of Prozac, and then after the treatment of Prozac. And if the null hypothesis were true, if there were no relationship between the variables, the independent variable is not affecting the dependent variable, then we would expect that the mean would not change. That initial mean that we had before treatment, which was 26 on the Beck Depression Inventory, will also remain at or about 26 after we've administered the treatment. In this case, it might be the SSRI, that is Prozac. Okay, so that would be the null hypothesis. Alternatively, we can look at the H1 and do something very similar. We'll start out with the baseline population before we've administered the treatment, and we might have our standard mu of 26 in this case. Then we administer the treatment, and what we might observe is something other than a mean of 26, something perhaps that differs significantly from 26. For the moment, in this particular diagram, all we're saying is that the post-treatment mean will be something other than 26. We're not making a directional prediction at the moment. We're not saying that the mean is going to be higher or that the mean is going to be lower. We're just saying that we have a mean that's going to be significantly different from 26. This would argue against the null hypothesis, which would state that there's no relationship between the variables. The null hypothesis is always stated in terms of equality of means. The pretest mean, in this case, would be equal to the post-test mean. Over here, we would have a refutation of that. Okay, so after we've stated our hypothesis, we have 3 steps to go. The second of these 4 overall, and the second one is that the hypothesis testing will involve setting the criteria for rejecting the null hypothesis. Okay, so we need to have some kind of boundary. A moment ago, were calling for a mean of 26 pre and post treatment, but we need to know how different the mean would actually have to be for us to say that we're confident in rejecting the null hypothesis. Just how different would that be? This is sometimes called setting the alpha level, and we'll learn that the alpha level is associated with something called a type 1 error that we could be making, but we won't get ahead of ourselves. We'll just plant this notion that we are setting some kind of boundary that's going to be related to something called an alpha level. Okay, the third step of the 4 involves obtaining sample data, and we can obtain some sample data by using a questionnaire, some kind of survey mechanism. We can do this experimentally, we can do this observationally. However it is that we get our sample data, it's best to obtain those data after we've first established what the hypotheses are, and secondarily, establish what the boundary conditions are using that alpha level. How different from 26, for example, would the experimental group have to be? And we want to do that all ahead of time so that we don't have any biases after the fact, and we're not inclined to just nudge the cutoff criteria one way or the next because that happens to be convenient for what we've observed in our sample. Here's the 4th and final step. We have to decide between 2 alternatives, and I mentioned earlier that we have this binary choice. We can either reject the null hypothesis or we can fail to reject the null hypothesis. Those are the 2 choices that are available to us. We don't state that we've proven the alternative hypothesis. Okay? We try to remove from our vocabulary the word prove or proven or proved. We want to get rid of those. We typically reserve that in science only for things that are mathematically proven by way of a proof that you might have done, for example, in high school for the Pythagorean theorem. In empirical sciences, the word prove is actually too strong. It's also a bit of a logical error to say that we've proven something, and more on that when we end today's session on a topic called Modus Tollens. Okay, but we won't get too far ahead of ourselves. Okay, these subtleties in logic, this refraining from the word prove and sticking to this notion of either rejecting the null hypothesis or failing to reject the null hypothesis. These subtleties in logic are important in science and also in the US legal system. In an earlier video, we had talked about some important parallels that exist between the legal system on the one hand and the scientific method on the other hand, and we'll return to some of those in today's discussion. Note that jurors are not asked to decide if a defendant is innocent. Instead, jurors essentially are deciding to retain or to reject the null hypothesis. And in our legal system, at least within the United States, the null hypothesis is that the defendant is not guilty. Notice that we don't say that the defendant is innocent. Typically, we say that the defendant is not guilty. And jurors are supposed to stick with that null hypothesis until there is substantial evidence to reject it. Usually we use the qualitative standard as evidence beyond a reasonable doubt. And as we've said before, in science we also have that kind of a standard, evidence beyond a reasonable doubt. And you'll see in just a couple of moments something that you might remember from Intro to Psych, that the standard is set numerically, and it's at something like a 0.05 level, a 0.05 probability, which is going to actually represent the alpha level that we referred to a moment ago, and that we'll describe in greater detail in just a few moments. So scientists are really doing something very similar to what jurors are doing. Okay? Let's see if we can schematize a decision matrix that a juror would have to go through, and that describes juries typically quite well. And then we'll see if we can tweak it just a little bit so we can understand how scientists use a similar kind of decision matrix. So if you're on a jury, your job as the juror is to figure out what was going on in the actual situation. You're presented information after the fact, and you have to find out whether the defendant had committed a crime, over here in this column, or whether the defendant did not commit the crime of which the defendant is being accused. Okay? That's what you're trying to decide, and here's going to be your verdict. Your verdict could either be guilty or not guilty. Let's take the top row first. If you decide, you as the jury, decide that the defendant is guilty, and in fact the defendant had committed the crime, you'd be making a correct verdict, and that would be good news. Right? On the other hand, if you decide that the defendant is guilty, when in fact the defendant did not actually commit the crime, you're making what we would describe as a type 1 error. In our legal system, this would be a travesty of justice, and you might be sending an innocent person off to jail, or even worse, in some states you might be sending an innocent person off to a death sentence. Okay? So this is a relatively egregious kind of error, and you'll see it has a parallel in the sciences also. Right? Now let's drop down here to the bottom row, and we'll ask about what's going on in the jury's verdict if the jury says not guilty. Okay? Well, if the jury says not guilty and the defendant actually did not commit the crime, that would be good. Okay? We got that one right. On the other hand, if the jury says not guilty, when in fact the defendant actually had committed the crime, then this too would be a travesty of justice, although it would be a different kind of travesty of justice. We would have missed the opportunity to maybe put into jail the criminal who had actually committed the crime. Okay, so we have different kinds of errors, different ways of being correct. Now what we can do is leave largely the same structure here, but we'll just tweak the diagram such that it now corresponds to your decision making as an experimenter when you're running some kind of test and you're evaluating the null hypothesis. Remember that the null hypothesis calls for the equality of means between the two groups that are being tested. It's basically saying that there's no relationship between the independent variable and the dependent variable, or no correlation between the variables of interest. Okay, so you're the experimenter, and you're trying to figure out, for example, whether Prozac really works or not. Okay, so the actual situation might be that there is an effect of Prozac, okay, and that HO is false. HO is the null hypothesis. Okay, and what we can say then is that if we have a null hypothesis and there's an effect that exists, if you as the experimenter reject HO, that's a correct decision. Okay, you did that just right. If you reject HO when in fact there was no effect there, then you've made an error. We would call that a type 1 error. We sometimes call this a false alarm, and I hope you'll make a note of that. I hope that you'll put down on your PowerPoint lecture notes that this is a false alarm. Okay? And that's what occurs in this particular section of the decision matrix. Let's drop down now and understand what happens when you fail to reject, which is to say retain the HO, or the null hypothesis. If you're retaining HO and the effect actually exists, you've actually made a type 2 error. You've missed the effect. Okay? On the other hand, if there is no effect and you've retained HO, you've done what is correct. Okay? So there are different ways of being correct, different ways of being incorrect. We call these false alarms and these misses, as we'll describe in just a moment. Okay, so in this slide we're going to summarize in a different format the information that we had in the last slide, because through the rest of your scientific careers you will see this kind of terminology. And even if you don't go on to science, I hope that this will inform your everyday thinking, because there will be many times in your professional lives and in your personal life that you will have to make some kind of dichotomous decision to either reject or retain a given assumption. And you'll now be able to more precisely think about those kinds of dichotomous decisions. Dichotomous meaning there's two possible outcomes. Okay, let's talk about the errors that we can make, and we introduced this a moment ago, the type 1 error. An error in statistical inference, and remember that we're trying to draw an inference about the population based on the sample, so a type 1 error is an error in statistical inference that occurs when a null hypothesis is true but is rejected. We're seeing too much into the data. Okay? This is a type 1 error, and I hope you'll make a note here as well that this is a false alarm. Okay, now we can begin to describe the probability of making a type 1 error by assigning it a unique symbol, and we typically do this by using the Greek letter A, or alpha, the first letter of the Greek alphabet, to correspond to the type 1 error. And that's easy to remember because alpha is the first letter of the Greek alphabet and it goes with type 1. The second letter of the Greek alphabet, beta, goes with type 2, so that should be very intuitive to you. Recall that the type 2 error is an error in statistical inference, as we're doing our inferential statistics, that occurs when a null hypothesis is false but is retained. Okay? So not seeing enough into the data. And we can talk about that probability and express it using the symbol beta, the probability of making a type 2 error. Okay, let's see if we can give you one example of each of these different kinds of errors by something that might occur to you in everyday life. So it might be that you're in your room with your roommate, and your roommate begins to sniff and says, do you smell something burning? So you take this deep inhalation and try to see if you can determine from your sense of smell whether something is burning or not. So you take this deep inhalation, and you say, yes, I think something is burning. I'm going to pull the fire alarm. Okay? Let's pretend that there really was nothing burning, but you believe that there is something burning. You will have pulled the fire alarm in error. That is, there really was no effect, nothing to get excited about, and yet we pulled the fire alarm nonetheless. That would be the equivalent of a type 1 error. Okay? And that probability of that type 1 error would be expressed by the symbol alpha. Remember that these probabilities range between 0 and 1 inclusive. Okay? Let's take the reverse scenario. Your roommate says to you, do you smell something? Okay? And in this hypothetical, something really is burning, and you're going to try to detect that. You take your deep inhalation, and you say, I really don't smell anything. Okay, now in this case, there really was an effect there, so to speak. There really was smoke to be detected, and yet you missed it. So we can think of this type 2 error as a type of miss. There really was something, but we failed to detect it, and we can describe that by the beta probability. Again, probability is going between 0 and 1 inclusive. Okay, so why don't we see if we can now begin to extend on what we've already learned, and see if we can address these two pop quiz questions. First, explain what is meant by the phrase sensitivity of an experiment, with an emphasis on the word sensitivity. Okay? And then secondarily, identify the 3 factors that determine the power of a statistical test. So here's an issue of sensitivity, here's an issue of power. We'll let you address those questions and stop the video. Okay, welcome back. We're now going to build on what we've been describing so far, and we'll see how we might go about evaluating hypotheses. So in the previous section, we noted that scientists typically have to decide between 2 types of possible errors, the type 1 error and the type 2 error. The type 1, again, would be the false alarm. The type 2 would be the miss. So the bad news is that when we're engaging in this evaluation of hypotheses, we might be making an error. And that seems like a downer to a lot of us, because we want to typically get things right. What I do love about science, though, is that we're very open about the kinds of errors that we can make. And we even have names for them, type 1 error, type 2 errors. We even have probabilities, as we'll mention in just a moment. The good news is that we can at least specify the probability of making any one of these errors. So we take error making very seriously in science. We are not so arrogant as to claim that we have truth with a capital T. Instead, we talk about the probability of a particular hypothesis, maybe the null hypothesis, being correct or incorrect, and whether it's disconfirmed or not disconfirmed, and we can specify the probabilities associated with each of those. So, yes, we might be wrong, but we know the probability of being wrong, and we can quantify that risk. And the way that we go about quantifying that risk, the risk of making these different kinds of errors, is we take advantage of the Gaussian distribution. Remember from an earlier video that the Gaussian distribution has certain mathematical properties that we typically know by looking at z-scores. Remember that we had the z-score in the center of the distribution corresponding to 0, and those to the left had negative values, those to the right had positive values. And we know something about the proportion of the population that falls between, say, a positive z-score of 1 and a negative z-score of 1. We know that 68% of the population falls in there, and we know other values at any given point in the Gaussian distribution. It's a nice feature of the Gaussian distributions, just like we know something about the relationship between the sides of a right triangle through the Pythagorean theorem. We can take advantage of Gaussian curves to talk to us about different kinds of probabilities. In particular, we can determine whether a particular score falls on the so-called critical region. Okay? And we can define the critical region as the area in a distribution that contains extreme scores that are very unlikely to be observed if the null hypothesis were true. So that sounds like a mouthful. Why don't we see if we can get a picture going and see if we can understand it. Okay, so we'll use for a moment the example that we've had during this entire video of looking at Beck depression inventory scores. And we said that the mean of the depressed population might be 26, and that the null hypothesis would say that if you were to treat a sample with Prozac, you wouldn't get anything much different from 26. The means would be equal. There's no effect of Prozac. That's the prediction from HO, the null hypothesis. Okay, let's see if we can tie that now to a Gaussian distribution. In this Gaussian distribution, you might think of there being a probability axis over here, although it's not shown in this graph. The most probable scores are right toward the middle, 26, and then we might get a fair number of scores a little bit higher than that, a little bit lower than that, but very rarely do we see scores that are very much more extreme on the high end or on the low end. This gives us the nice bell-shaped curve. On the x-axis, we're plotting first the raw score that we get from the Beck depression inventory, 26 at the center, and then much lower scores down over here, much higher scores up this way. As we said before, we can take any given raw score and we can convert it into a z-score. A z-score is said to be dimensionless. It's not all about a particular unit. It's this number of standard deviations. Here, we're at the center of the distribution. Our z-score is 0. We have positive z-scores up this way. We have negative z-scores this way. We know something about the proportion of scores beyond a given point on the right or beyond a given point on the left. Okay? So the critical region is going to be way out here on the extremes, and typically we use a cutoff of 0.05 as our alpha level. So we might take the extreme-most 5%, 2.5% up that way, 2.5% down this way, and we would say that's the extreme-most 5%. In between those extremes, we have the more typically occurring 95% of all the means that we might observe. So we can actually have two x-axes here, one that carries the raw score, and one that carries the z-score, and the z-score is helpful because we can tie those using different kinds of Excel commands back to particular kinds of probabilities in a Gaussian distribution. So the critical region is shown here in pink, and we're really wondering whether the mean of the experimental group that has received Prozac is going to be pretty typical in its mean, or will it be maybe more extreme in its mean? Okay, so the critical region goes by a few different names. We might call it the critical region, but also the rejection region or the region of rejection. Any of those, or any near permutations of that, would be the same region, those extreme portions of the Gaussian distribution. So if a sample mean falls in the critical region, the null hypothesis is rejected. That's typically the rule that we use. So here it is again, our Gaussian distribution. You can see that we have a sigma of about 0.8. Okay, so we're getting a standard deviation in the population of about 0.8 plus or minus that from that 26 central score. Okay, and here's the z-score corresponding to that. So sample means that fall all the way down here or all the way over here would be said to be statistically significantly different from this mean. And we would have a statistically significant effect if we were to empirically observe means all the way out here or means all the way back here. Okay, so yes, we might make a type 1 error, but typically the probability of such an error is just 5%. And in many cases, we distribute that 5%, 2.5% up here, 2.5% down this way. That is, we say that our alpha level, and you'll recall that the alpha level is the probability of a type 1 error. Stated another way, the probability of a false alarm. So we set our alpha level to 0.05, meaning that we have only a 5% chance of rejecting a null hypothesis that should have been retained. Okay. In some cases, we might want to minimize the risk of a type 1 error. We could choose an even more stringent alpha level. So typically, we're using this range, okay, that corresponds to the alpha level of 0.05. So 95% of the scores are within the center of this distribution, and the 2.5% and 2.5% up that way make up the most extreme 5%. But maybe a 5% risk of a type 1 error is too much for some researchers to bear. And they want to be a little bit more inferentially cautious. That is, cautious in their inference or their conclusions. They might want to reduce the risk from 5% to, say, something like 1%. How would you go about doing that? Well, you can set your alpha level, the probability of a type 1 error, from reducing it from 0.05 down to 0.01. But to do that, you're going to need to observe more extreme scores, or scores that are falling something like 2.58 z-scores above or 2.58 z-scores below the middle z-score of 0. And that would have to be really quite an extreme score to achieve statistical significance at the 0.01 alpha level. You can go even further still. You can say, I'm not interested in 5 chances out of 100. I'm not even interested in 1 chance out of 100. I'm interested in an extremely stringent alpha level of 0.001, 1 chance in 1,000. Okay? And in order to make that claim, you'd need pretty strong evidence. Specifically, you'd have to go out and make an empirical observation of your treatment group having a mean way out here, something like 3.30 standard deviations above the mean or 3.30 standard deviations below the mean. Those are very extreme scores. They can happen by chance, but they can only happen by chance with knowable limits that are specified here by the alpha level. So you can imagine how difficult it is to get these really extreme scores that have really, really low alpha levels. And to help us remember that, some of my students have enjoyed this picture. Imagine that your job is to make it underneath this alpha level, okay? And if that alpha level is 5 units high, that's pretty challenging. If you bring it all the way down to just 1 unit, kind of like we have, pardon me, okay, we typically have an alpha level of 0.05, and that's challenging enough. If you bring it all the way down to 0.01, that's even harder. Down to 0.001, that's really quite a bit harder. Same thing is true for this particular dance. If you can do the limbo under 0.05, that's pretty good. If we lower the bar and you have to do it under 0.01, that's really impressive. If you bring it down all the way to 0.001, that's extremely impressive. And so it is in science. If you can show that you have an effect that has significance at the 0.001 alpha level, you have an impressive story to tell. You've made a very convincing empirical demonstration. Okay, so what I'd like you to do now is jot down what kinds of things you found to be particularly clear about our discussion of evaluating hypotheses and what remains unclear. We'll ask you to stop the video, but don't turn it off just yet. We're going to come back in a moment, and we're going to have a little further conversation about hypothesis testing and the logic that underlies it. Okay, welcome back. And what we'll do now is have some conversation about the logic of hypothesis testing. And we'll take a look at this information on the board. We're going to learn about a structure of logic that logicians, it's a branch of psychology, logicians have introduced, and it's called Modus Tollens. Can you say it with me? Modus Tollens. There you go. I knew you could say it. Okay? And modus tollens translates into something like denying the consequent. So let's see if we can understand what is meant by denying the consequent. We're going to begin by talking about a type of structure that we've introduced once before. It's called a conditional statement. You might remember that in Excel, we worked with a conditional statement that went something like this: equals if, and then we put in some statement. If that were true, then we did one thing. If it were false, then we did something else. A conditional statement generally takes the form of if this, then that. Okay, that's our conditional. So in the structure called modus tollens, we have if P, then Q. The item that's coming first in that sequence is called the antecedent. In this case, it happens to be P. That's a variable or a placeholder just for the moment. And then the item that's coming second is called the consequent. The idea being that this follows as a result of that. Okay, that would be the logic. So if antecedent, then consequent. More simply, if P, then Q. I really like doing this with P's and Q's to get the ball rolling because it reminds us that as a liberal arts student, your job really is to become an all-purpose problem solver. You might be using some of this logic to solve problems in psychology now, but you can use this in any of the other sciences, and you can use it to solve all kinds of challenges that might arise in civic endeavors and in community affairs, in issues relating to your family, or issues relating to your child's education, or your personal life, whatever the case might be. We hope that you will become an all-purpose problem solver. So we always like to introduce these first in these placeholder variables, and then give you some examples that you might be able to slide in so you can see just how general a problem-solving technique this is. So we start out with a conditional statement in Modus Tollens. If P, then Q. What we're going to do is deny the consequent in Modus Tollens. So we're basically going to get to this little squiggle, which is called a not sign informally, not Q, so we're denying Q. And according to Modus Tollens, if you can deny Q, then you can deny P. So the overall segment would read like this. If P, then Q, not Q, therefore, and these three dots in a triangle correspond to the therefore symbol, not P. Okay? If P, then Q, not Q, therefore not P. We deny the consequent, and this permits us to deny the antecedent. Okay? That's the generic structure. And some people follow that well. Other folks find that to be a little bit abstract, and they would benefit by an example. So we're going to do 3 examples, and we'll save hypothesis testing for the last of the 3 examples. Let's start out with something that's really very intuitive, and it speaks to maybe a cause and effect relationship. Okay? So, very simple example. If P, then Q, we'll do it this way. If it's raining, then the street is wet. Okay? If P, then Q, if it's raining, that's the antecedent, then the street is wet. Let's say that you and I engage in an empirical investigation of the consequent, okay, that the street is wet, and we go out and we examine the street, and we examine it very closely, and we find that the street is bone dry, okay, not Q. The street is not wet. We can then infer from that that it is not raining. Okay? If it's raining, then the street is wet. The street is not wet, therefore it isn't raining. Okay? A pretty straightforward cause and effect kind of evaluation using the correct logical structure called Modus Tollens. Okay? Well, that might be too straightforward. Somebody might say, well, I need a little more to see why this thing is helpful to us. So let's see if we can give a different example where we might understand the relations between variables that might be shown by way of a Venn diagram. And still, Modus Tollens will hold up for us. Okay, let's say that we're interested in investigating this particular statement. Let's say that an unidentified student is pregnant. Okay? If a student is pregnant, then it would follow that that student is female, Q. So if P, then Q. Okay? At least this is true for our species. A biology student might be able to generate a type of species for which that isn't true, but for the human animal, if the student is pregnant, then the student is female. Okay? Let's see if we can get that by diagram. Here's pregnant. Okay? Here are all the pregnant students, and here are all the female students. Okay? And what we can say then is if the student is pregnant, then they're participating in this wider idea, or this wider category that we call female. Okay, that would work. Now, we said that we'd always engage in some kind of empirical investigation, and let's say that we find a particular student who is not Q, which in this diagram would be not female. That student would be out here, for example, not landing within the category of female, and then we could safely conclude that that student would not be pregnant. Okay? So, if the student is pregnant, then the student is female. If the student is not female, then the student is not pregnant. Hopefully you can see that Modus Tollens works for us again, even when we're thinking about these concentric circles that we might diagram by way of a Venn diagram. Okay? All right, let's see if we can do one more example. And in this last example, we'll talk about the earlier case of depression and whether Prozac is working for depression. You'll recall that we had a Beck depression inventory, and we had a mean score before the treatment began of 26. So let's see if we can get a Gaussian distribution, and we'll see if we can investigate HO, the null hypothesis that says that there's no effect of Prozac, and that the mu's will be equal, that the mean of the treatment group will be equal to the mean of the control group. So here, once again, is our Gaussian distribution. And we can draw this in z-scores, or we can draw this in raw scores. For simplicity, I'll draw it in raw scores. Okay? So my z-score here would be 0. My raw score would be 26 from the Beck depression inventory. That's the BDI. And you might remember that we have these critical regions that are on the most extreme 5% of the distribution. So we have one way up here, we have one way down here. And what the null hypothesis says is that there's a null effect of Prozac. So that if you have a control group that has a mean of 26, you can give Prozac to an experimental group if you want, but the mean is still going to be about 26. And of course, there's some wiggle room here in the null hypothesis. It might not have to be exactly 26, but it would be similar to 26. It wouldn't be extremely different. It would not be significantly different. Okay? So the null hypothesis would say that the treatment group should have a mean that's similar to that of the control group, and we would get a relatively typical mean, not an atypical mean, not a mean that's significantly different. That would be the case. Okay? So if the null hypothesis is true, then the treatment group should have a typical mean, something in the inner 95%. Well, let's say that you and I do an empirical investigation, and we get some good news. We find out that we get much lower Beck depression scores in those who are treated with Prozac. Okay? So we now get an atypical score, and basically then we've refuted the prediction of the null hypothesis, and that permits us to reject the null hypothesis, not Q. So if the null hypothesis is true, P, then we would expect a typical mean, Q, not Q because we observed a highly atypical mean, in this case a very, very low mean, which means we've reduced depression. That's pretty good. So we can reject, in that case, the null hypothesis. So this is the logic that underlies hypothesis testing. It's based on this formal structure called Modus Tollens, and we hope that that's clear to you, but we'll give you the opportunity now to jot down what is clear or what is not so clear and bring that information into class. See you in class.